Hey guys, IBM is here with this is going to be episode 33 or part 33. I mean 23, not part 33, part 23 of magnetic fields and electromagnetic induction. These are past paper questions for 9702 from 2001 up to 2025. State the type of field or fields that may cause a force to be exerted on a particle, that is, if the particle is not charged, we can assume it has mass, but it has no charge and it is moving. As long as it has no charge, whether it is moving or not, the only force acting is gravity. So the only force acting here is gravitational force. So the force which will cause the field which will cause the force is the gravitational field. So this is going to be gravitational. So the particle is charged and stationary. Already it has mass, so there is gravitational. The particle is charged and moving, already it has mass, so it is gravitational. Gravitational force acts on everything which has mass. So then we come back. If it is uncharged, there is no electric field, there is no magnetic field, even if it is moving. If it is charged and stationary, as long as it is charged, it experiences an electric field. So here there is also electric field. The electric field. But because it is stationary, magnetic force does not act on a stationary charged particle, so it's only electric field. The particle is charged, already it had mass, so there was gravitational. Since it is charged, there is also electric field. And because it is moving at right angles, there is also magnetic field. If it was moving parallel, then if it was moving parallel to the field, then the magnetic field wouldn't be there. Because for a magnetic force to be acting on a particle, the particle must be moving with a velocity having a component perpendicular to the magnetic field. A particle X has mass 3.32 times 10 to the power of minus 22 kilograms, charge positive 1.6 times 10 to the power of minus 19 coulombs. The particle is traveling in a vacuum with a speed 7.6 times 10 to the power of 4 meters per second. It enters a region of uniform magnetic field that is normal to the direction of the particle. Because the field is normal to the direction of the particle, there is a magnetic force. And when you look at the diagram, the magnetic force must be acting towards the center of the circular path. The particle travels in a semicircle of diameter 12.2 centimeters, so the radius is 6.1 centimeters. For the uniform magnetic field, state its direction. For the uniform magnetic field, state its direction. So at entrance here, the particle is moving towards, of course, the force is towards the center, so the force is in that direction, the velocity is in that direction. Then by Fleming's left-hand rule, you notice that if you use Fleming's left-hand rule, I think the direction of the field is out of the plane of the paper. Second finger, direction of the velocity, that is towards the top of the page, and the thumb towards the center of the curve, that is towards the right. When you try to use your left hand with the second finger towards the top of the page and the thumb towards the right hand side, you notice that the first finger, if the page is on your table, the second finger points towards the top of the page, that is away from you. The thumb towards the right hand side. The only way you can twist your left hand is when the first finger is pointing towards the roof, which is actually out of the plane of the paper. So that is out of the plane of the paper or the plane of the page. Out of the plane of the page. Okay. So By Fleming's left-hand rule, the magnetic force is perpendicular to the direction of the particle and the field. So with the second finger pointing in the direction of the particle, which is on entrance, and the thumb in the direction of the force, which is towards the center of the circular path or towards the right, then the first finger must point out of the plane of the page. That is, it is out of the plane of the page. It is not upwards, not towards the top of the page, but out of the plane of the page. So if the page is on your table, I say that this is, if the page is on your table, this is the first finger is going to be pointing towards the roof. If you are trying to use the Fleming's left-hand rule, the first finger, which shows the direction of the magnetic field, is going to be pointing towards the roof. Then calculate the magnetic flux density. So the magnetic force provides centripetal force. So that means B QV is equal to mv squared over r. So making B the subject, B is going to be mv divided by r times q. Substituting, the mass was 3.32, the charge is 1.6, the speed is 7.6 exponent 4. So this is 3.32 by 10 to the power of minus 26. The speed was 7.6 times 10 to the power of 4. The radius was 6.1 times 10 to the power of minus 2. And the charge was 1.6 times 10 to the power of minus 19 coulombs. So 3.32 exponent minus 26 times 7.6 exponent 4 divided by 6.1 exponent minus 2 divided by 1.6 exponent minus 19. So that is 0.26 Teslas. A second particle Y has mass less than that of particle X in B and the same charge. The mass is less. It enters the region of uniform magnetic field in B. So B is the same. With the same speed, V is the same. Initial path as particle X, along the same initial path as particle X. On the figure, draw the path of particle Y in the region of the magnetic field. So we have already seen that R equals to mv, making R the subject. R is mv divided by B times Q. V is the same, B is the same, it has the same charge, but a smaller mass. So R is directly proportional to M. If the mass is small, it means the radius of the path is also going to be smaller. So it means the new path, the path for Y should have a smaller radius. Therefore, the path is going to be inside this one here. So I will draw a new path of a smaller radius. So this is going to be the new path. This is going to be the new path of Y. So this is for Y, particle Y. A solenoid is connected in series with a resistor as shown in the figure. As the magnet is being moved into the solenoid, thermal energy is transferred in the resistor. Use laws of electromagnetic induction to explain the origin of this thermal energy. Okay, so we have a complete circuit here. So if there is a change in flux linkage of the coil, an e.m.f must be induced in the coil and the current should flow in the coil. And if a current flows through the resistor, we expect that power is going to be dissipated in the resistor. So there are two ways of thinking about this. The first one, the turns of the coil cut the magnetic field of the moving magnet, which gives rise to an induced EMF or a current in the solenoid. The induced current is also going to create a magnetic field around it in the solenoid, and this magnetic field is going to oppose the motion of the moving magnet. That is in accordance to Lenz's law. The work done to move the magnet into the solenoid against the opposition and the induced current is what is going to give an effect or a heating effect in the what? In the resistor here. That's one way of thinking about this. Of course, the first part where the moving magnet causes a change in magnetic flux linkage, that is actually Faraday's law, because this will give a rise to an induced EMF. So I'll simply say that the turns of the solenoid, cut the magnetic field of the moving magnet, which gives a rise to an induced EMF. Stroke current in the solenoid. And this is Faraday's law. The induced current or the induced EMF, the induced current in the solenoid also creates its own magnetic field. The induced current also creates a magnetic field. In the solenoid. That opposes the motion of the magnet. Of course, this is going to be Lenz's law. As you try to bring the magnet closer, the induced EMF is going to create a magnetic field which opposes. In other words, when you bring the magnet towards this end will be north, the other one will be south, to oppose the bringing of the magnet. So the induced current also creates a magnetic field in the solenoid that opposes the motion of the magnet. And so the work done to move the magnet into the solenoid the magnet into the solenoid against the opposition or the opposing force, against the opposition and the induced current gives a heating effect. A heating effect in the resistor. So there is work done to overcome the opposition as you try to move the magnet into the solenoid. And also the induced current which flows in the solenoid through the resistor is what is going to cause a heating effect in the resistor. Okay, so that is how we can explain that using the laws of electromagnetic induction. Two long straight wires P and Q are parallel to each other as shown in the figure. There is a current in each wire in the direction shown. So there's a current in each wire in the direction shown here. The pattern of the magnetic field lines in a plane normal to wire P, because the plane is perpendicular to wire P. The current in the wire is also shown. So it means the current is perpendicular to the magnetic field because the magnetic field is in the horizontal plane and the wire is in the vertical plane. Draw arrows on the magnetic field lines in figure 8.1 around wire P to show the direction of the field. So because we use the right hand grip rule, which I illustrated here, try to grip the wire in the direction of the current with the thumb pointing in the direction of the current, the fingers fold in the direction of the magnetic field. And you notice that they are folding anti-clockwise. So this is going to be in this direction here, anti-clockwise. So we imagine gripping the wire in our right hand. The field lines are concentric circles as shown, but the fingers fold in the direction of the magnetic field. Determine the direction of the force on wire Q due to the magnetic field from wire P. So we want the direction of the force on wire Q. Now let us imagine there was one magnetic field line around wire P which could spread up to the position of wire Q in this pattern here. Remember the field lines are in that direction there. So it means the magnetic field here will actually be a tangent into the page. A tangent into the page. I couldn't demonstrate this clear into the page, but I demonstrated it with my left hand. The magnetic field here is going to be a tangent to this curve into the page. It's a tangent into the page shown by this first finger here. So if B is a tangent into the page and the current is upwards, using Fleming's left-hand rule, with your first finger pointing onto the page and the second finger pointing in the direction of the current, which is towards the top of the page, the thumb is going to be pointing towards the left. Therefore, the arrow we are looking for is going to be this one here. So this is the direction of the force. That will be the direction of the force. So determine the direction of the force on wire Q due to the magnetic field from wire P. So this is to the left. You could say to the left, or you could say towards P, towards wire P. The current in wire Q is less than the current in wire P. State and explain whether the magnitude of the force on wire P is less than, equal to, or greater than the magnitude of force on wire Q. Earlier on, we mentioned that the force is directly proportional to the current in wire P and current in wire Q, and the product is the same for both wires. So the force is the same. Or by Newton's third law, the force is equal but opposite. So I could say by Newton's third law, by Newton's third law of motion, the force on P is equal but opposite to the force on wire Q. So equal but opposite to the force on wire Q. So that is by Newton's third law. The force is equal but opposite. Alternatively, you could say the force on each wire is proportional to the product of the two currents, or the force on each wire is proportional to the product of the two currents. The force on each wire is proportional to the product of the two currents, and so the forces are equal in magnitude. So whether the currents are different, the forces are equal in magnitude. Okay, define magnetic flux density. Define magnetic flux linkage. So you can define it by a formula. You would say flux linkage equals to bands, or NBA, sine theta, and then you define this. You would say B is the magnetic flux density, then A is the area of the coil, and N is the number of turns. What is very important is theta. Theta is the angle between, because I said sine theta, so the angle is between the area and the magnetic field, or the angle between the magnetic field and the area. Or if I don't want to say that, I'll just define it like this. Because I can eliminate theta by saying B is perpendicular to the area. So I would say the product of number of turns of a coil, magnetic flux density, and the area. And the area normal to, or perpendicular to, and the area normal to the magnetic field. In other words, you are saying magnetic flux is BAN, but the area should be perpendicular to the magnetic field. So this is also an easy way of defining magnetic flux linkage. A solenoid of diameter 6 centimeters and 540 turns is placed in a uniform magnetic field as shown here. So this is the solenoid. The magnetic field is towards the right. The diameter is 6 centimeters. Number of turns is 450. The variation with the time t of the magnetic flux density is shown here. So we see that magnetic flux density increases up to around, which time is this? I think that is 2.4. And then this is, that is 6. Calculate the maximum magnetic magnitude of the induced EMF the solenoid. So where do we have maximum? So induced EMF is directly proportional to the gradient. The induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is actually going to be directly proportional to the gradient. So where is the gradient steepest? I think the gradient is steepest at between t equals to 6 seconds and t equals to 7.2 seconds. So that means maximum EMF is going to be induced in this region here. In this time interval here. So did I say explain? No, but I've explained. The induced EMF is directly proportional to the rate of change of magnetic flux linkage, and the rate is directly proportional to the gradient of magnetic flux density against time. Therefore, the EMF is going to be maximum where the gradient is steepest. That is between t equals 6 seconds and t equals 7.2 seconds. And we know that the induced EMF is going to be equal to NBA, or it is change in B times A times N times A times N, then divide by time. So, and of course we know that the area, they gave us the diameter. The area is pi r squared, where diameter was 6, so the radius is 3 centimeters. So the EMF is going to be the gradient here, delta B over T, which is going to be change in B is 250 minus 0. So I'll just write 250 times 10 to the power of minus 3 because it is in milliteslas. The area is going to be pi times the radius, which is 0.03 squared, then times the number of turns, which was 450, then divide by time, which was 7.2 minus 6, that is in seconds. Okay, from the calculator I have 250 exponent minus 3 times pi times 0.03 squared times 540 divided by 7.2 minus 6. So that is 0.318 or 0.32. So this is 0.32 as the maximum magnitude of the induced EMF. A thin copper sheet X is supported on a rigid rod so that it hangs between the poles of a magnet as shown. Okay, so it is supported. So let's say one pole is north, the other pole is south. So it can rotate, it can swing in that pattern, it can oscillate in that pattern. Sheet X is displaced to one side and then released so that it oscillates. A motion sensor is used to record the displacement of X. So a motion sensor is used to record the displacement of X. Okay. So it was a full sheet. Now here, second thin sheet, copper sheet Y replaces sheet X. Sheet Y has the same overall dimensions, that is length and width, but it is cut into the shape. So the other one was full, but this one is cut into this shape. The other one was full like this. This one is cut into this shape. This was X. The motion sensor is again used to record the displacement. Note that both are in the magnetic what? Let's say this is north-south. North-south. The graph in the figure 9.5 shows the variation with the time t of the displacement S of each copper sheet. State the name of the phenomenon illustrated by the gradual reduction in amplitude of the dashed line. So we see gradual reduction in amplitude, that is of course light damping. Gradual. It's not just damping but light damping because the amplitude is gradually decreasing. So that is light damping. can find that under simple harmonic motion and oscillations. Then deduce which copper sheet is represented by the dashed line. Explain your answer using the principles of electromagnetic induction. So when I look at the two graphs, when I look at the two graphs and the two diagrams where the other one was cut um, into this shape here where there are empty spaces, it means for Y, the area of overlap or the area over which the magnetic field lines are intercepted has been reduced compared to this one here. Even though they have the same overall dimensions, look at the section which is in the magnetic field and compare with this one here. So the copper sheet cuts the magnetic flux, which causes an induced EMF, that is according to Faraday's law. And of course, the induced EMF may cause eddy currents in the copper sheet. The currents in the copper sheet are expected to dissipate energy, but then the amount of energy dissipated in this one here is going to be more than the amount of energy dissipated in this one here because of the spaces here that you could see. So the currents in X, the eddy currents in X can easily grow larger because of the sheet is continuous. Yet the eddy currents in the different sections of this may not easily combine to form a very large eddy current. So the damping here may be much smaller than the damping here, or the power dissipated in X because of the large eddy currents which grow up in X may cause more damping. So the currents in X are larger than currents in Y, so there is more energy dissipated in X as compared to Y. Therefore, the dashed line is most likely going to represent X. So this is going to be X, this is going to be Y. Or you could talk about the currents in the copper sheet causing a resistive force. In other words, the copper sheet cuts the magnetic flux, which causes an induced EMF. The induced EMF causes eddy currents in the copper sheets, and you say the currents in the copper sheet causes a resistive force. The current in X are larger than the currents in Y, so the resistive force in X is greater than the resistive force in Y. Therefore, this causes much more damping in X as compared to that in Y. Okay, so I'm going to give the two sides. So I'll say one. I said the copper sheet cuts the magnetic flux. Of course, as it is oscillating, the copper sheet cuts the magnetic flux, which causes an induced EMF. Of course, the induced EMF causes eddy currents in the copper sheet. Remember, X and Y are both copper sheets. Now, the currents induced in these sheets are going to be called the copper sheets because one, the copper sheet does not oscillate with the same speed through the magnetic field. Remember, oscillations, speed is maximum at equilibrium position and it goes on decreasing. Because the speed decreases, it means the magnitude of the induced EMFs also decreases, changes. So not the same magnitude of EMFs are induced in the copper sheets. Therefore, not the same magnitude of currents are induced in the copper sheets. And also these currents will point in different directions. That's why we call them eddy currents. So the induced EMF causes eddy currents in the copper sheets. Now, part one, we could say the currents in the copper sheet dissipate energy. The currents in the copper sheet dissipate energy. The current in the copper sheet dissipates energy. Of course, we notice because of the area, the shape of these copper sheets, the current, there will be more eddy currents here because of this being a continuous area compared to this one here. So the currents in X are larger, or the eddy currents in X are larger than in Y. So more energy is dissipated in X, resulting into more damping, thus the dashed line is X. The dashed line is X. Alternatively, I would write these two, and instead I would say the currents in the copper sheet cause a resistive force. That is in accordance to Lenz's law. And because there is a greater current in X, then the resistive force due to X is greater. The currents in X are larger than in Y. Why are they larger? There's a continuous area in X, so the currents easily add up to form a very large value compared to that in Y. So the currents in X are larger than in Y, so the resistive force is greater. In X, resulting into more damping. Thus, the dashed line is X. So the dashed line is still X. You consider resistive force. Okay. So let part 23 stop there. See you in part 24. Until next time. Bye bye.